When we're talking about liquids, it's a little bit harder to talk about forces like we would with a point particle or even a rigid object. If I have a little blob, this is a container full of water or a general liquid, and I have a little section of that I've just kind of imagined in my mind, and I apply a force to it, it doesn't behave like a point particle would. It wouldn't accelerate linearly in the direction of the force, and it wouldn't behave like a rigid object. It wouldn't rotate. What might happen is some of the water would squeeze off that way, some would squeeze off this way, and some would squeeze off that way. And so we have a difficult time trying to talk about forces in water. There are forces, they're definitely being applied. But what becomes easier is to think about how the force is applied over an area. So let's say I look at the base of this jar that I've drawn and just look at a little section of it. Okay, it's got some area on that, and I know that there's force pushing on it. There's water on top of it pushing down everywhere with this force. And what the container wall, that section of the wall, feels is this force spread out. We call that pressure. Okay, pressure is defined as the force per unit area. Okay, and so pressure is a little bit better of a measure because that's something that we can say there's a pressure at a point in the fluid. Whereas force, there are forces at points. It's just a lot harder to analyze them because the force against a container wall depends upon the force at each point on that container wall, and that might be changing. So force or pressure is defined as force per unit area. Now we can use that if we know the pressure somewhere. We can use that to say that force then is equal to pressure times area. And so that's something that's advantageous to us.